One final thing I want to get across before we go any further into this course, that sig figs, or significant figures, sets a limitation on the number of valid decimals in your answer. The classic illustration of this is okay, what you have here is the R, which is a universal gas constant used in virtually all of your gas law problems. Note that the limiting factor is the least valid number of component digits. For instance, if you put together a problem, and this is not a particularly complicated problem. It's 2.560 kilograms per meter second squared. All right, that's the pressure. The volume is 8.8 cubic centimeters, and the temperature is 275.15 Kelvin. When you grind all that out, realize that the significant figures in the answer is going to be dictated by the least number of digits provided in the problem, which is the 8.8. Now, if you can remember that up front, this will keep you out of trouble with significant figures. Okay? So I'm going to erase this because I wanted to make sure I got that across before we get any further along, and go into, I had a colleague many years before your parents were born who referred to the mole as a furry little critter. Now, this is homespun, but this furry little critter, the mole, is an invention, if you wish. Now, back when chemistry was being consolidated into one practice, you had a lot of problems to deal with. First, you had disparate measurement concepts. That's the reason they finally went with one standard measurement, the SI units, if you wish. And they also had a lot of different viewpoints on what constituted particles and numbers. So they came up with a universal accepted particle number. And the mole became a number of particles that constituted the number of atoms or molecules in a given atomic mass. So these particles, or a mole, is referred to as 6.022 times 10 to the 23rd particles, which is not used very much, atoms, which is used a lot, or molecules. Now, how does that come out for practical usage? Well, my favorite, of course, is always water. So let's use water as an illustration. Hydrogen, we'll say weighs 1 for all practical purposes in this problem. It actually is 1.00 something another. So we'll count it as 1 in this. And oxygen, we'll count as 16. Whole numbers are easy to mess with. If you want to go 15.999, it'll still come out, shake out pretty close. So we got hydrogen is equal to 1, and oxygen is equal to 16. If you combine them together for water, you have an atomic mass of 18 grams per mole. Now, the mole is an extremely important understanding, because when you see something written like that, you know that in 18 grams of water, you have 6.02 times 10 to the 23rd molecules of water. That's a big number. And it's purposefully stated that way, because one of the difficulties of understanding physics and chemistry in general is the large numbers of particles that are invisible to the naked eye. You can't see the molecules of water. You can't see the atoms, the components of the. We live in a pretty much plastic society, and the plastic molecules, again, very much organic or organometallic, are molecules, and each of the molecules contains hundreds of atoms. So even seeing the molecules that contain hundreds of atoms is impossible for the naked eye. So we need something that's understandable at a level of our viewing, and that's where the mole concept comes in. Okay, we'll take 100 grams of water that you drink for a small glass of water. All right, the way that goes is that 100 milliliters of water, which is a small glass, is equal to 100 grams of water, because 1 milliliter or cubic centimeter for water, those are all equivalent. So we want to know how many milliliters, how many molecules of water you are drinking when you drink a small glass of water. Now, this might be viewed as kind of a waste of time, but I don't think so. The way you do that is pretty straightforward. You take the 100 grams and divide it by the 18 grams per mole up here. The atomic or the molecular weight of water, and you come up with 5.55. 5.55 moles, or because we only have 2 sig figs in the 18, we'll go with 5.6 moles. Now, if you multiply that by 6.02, and in most instances, the 2 becomes 6.02. It's rare that it's taken out to the 6.02. 6.02 times 10 to the 23rd times, that's the number of molecules per mole, times the 5.6 moles. Notice the moles cancel out and you're left with molecules. So when you digest that and multiply it out, you find that when you drink a small glass of water, it's about 3.4 times 10 to the 24th molecules. So the next time you drink a small glass of water, realize you're drinking 3.4 times 10 to the 24th molecules of water. Is that material for your everyday life? Heck no. But it's kind of important in chemistry that you get a feel for the practical application of some of this. Now, I skipped over something up here, which I probably shouldn't have. To find the molecular weight of any compound, you add the sum of the components. So in water, hydrogen's 1, oxygen 16, there's 2 hydrogens, 16 plus 2 is 18. Now, that's really quite superficial, but if it gets more complicated, one of the substances that you eat every day that if you continue to eat it in large quantities is going to kill you, and I'll be sure that piqued your curiosity when I said that. And this is the substance that's destined to cause your demise. Sugar. Now, if we're trying to find out what the molecular weight of sugar is, we do it logically, look it up on a periodic table, and carbon, again, I want you to look it up. So everybody stop, take out your periodic table, find out what the atomic mass of carbon is. And you find it is 12. So you multiply the carbon 12 times the number, which is 12 grams per mole of, and that is 144 grams per mole. Well, it's just grams in this instance, because if we're looking for a mass for the whole thing. And then hydrogen is 1 times 22 is equal to 22 grams. And oxygen is 16 times 11. So again, depending on how you want to do this, I suggest you do this kind of stuff in your mind. They give you 176 grams. You add all this together, you 6 and 4 is 10, 12, 7, 4 is 11, 12, 13, 14. So it's 342 grams per mole for 1 mole of sugar. Now, most of you don't eat 342 grams of sugar a day. Thank goodness. Otherwise, you're not going to last real long. Sugar itself is, depending on the type of sugar, is dependent in buildup on how much exercise you get, how much energy you expend. And the type of sugar is important too. Cane sugar is actually better for you than complex corn-based sugar. There's a variety of reasons for that, and you'll have to check with your dietitian as far as the value there. Now let's take another problem, since we're working problems today. And again, I try to associate things that are part of your existence on a daily basis. Now, one of the hardening agents in water is calcium carbonate. So that's a 2- ion and a 2+, so it forms 1 to 1, or calcium carbonate. Now, calcium, the question here is, what is the, let's see how did I phrase this problem. The mass of any compound, okay. Now, calcium carbonate is kind of a neat substance because it's not only the hardening agent in water that, leaves the white streaks after the water dries, but it's a component of marble. It's a component of limestone. It's a component of chalk. It's a component of pearls, real pearls. And all those seashells you see lying along the beach, calcium carbonate, predominantly. So it's pretty, what we call ubiquitous. Ubiquitous refers to all-encompassing. It's everywhere. So we're dealing with calcium carbonate, and we got a sample. It's 4.86 moles of the calcium carbonate. And we want to know what the heck that weighs. To do that, you got to find out the molecular weight of the calcium carbonate. Go look it up. You'll find that calcium is 35.5 or 30. I would say stick with 35.5. You got 12 for the carbon, and 16 times 3 are 48. And if you add those together, it's more difficult to do it longitudinally than it is latitudinally. You'll get, let's see, that's right. It is not right. That's what I get for doing it. You got 5, 6, 7, 15, which is right, 5. And then 3, 4, oh, that's what I missed. 45, it's 55. 55.5 grams per mole. You notice mole has been shortened from MOLE to MOL because that's really what we use. So the molecular weight of calcium carbonate is 35.5 plus 12, which is 47.5, plus 48, which is, again, see, when you get old, you got to have a calculator all the time. So that's 47.8 plus 48 is 95.5. Let's see if I'm right. Again, longitudinally, I can do it much quicker. It is 95.5 grams per mole. Now, if we multiply 4.86 moles, no fair making fun of me because you got your calculators at hand, times the 95.5 grams per mole, which is the molecular weight of calcium carbonate. Again, the moles cancel, and if you multiply 95.5 times 4.86, all right, so it's 95.5, so we got 3 decimals. Should come up with about 463 grams. Now for sig figs on this, we have 3 sig figs, so 463 would probably be the correct answer based on your significant figures. Let's see if I did the math right. 5 sixes are 30, 5 eighths are 43, 4 fives are 20, 24. That's correct, so bring that down. 6 nines are 54, 8 nines are 72, 6, 7, 4 nines, 36, 43, so that's all right. 3, 4, 8, 11, 6 and 4 is 10, 12, 13, 5, 6, 4. So the math's right. And that's how you find the number of grams in 4.86 moles of calcium carbonate, the primary hardening agent of water. That's the mole concept, folks. Now, it's not hard if you keep straight in your mind that your basic tenet is the number of molecules or the number of atoms is always 6.02 times 10 to the 23rd for the mole. The mass is always based on whether it is an atomic substance or a molecular substance. Atomic substance, you can look it up on a periodic table. Molecular substance, you have to add up all of the mass of all of the molecules. Now, sugar here or calcium carbonate here is fairly easy. Sugar is a little bit more difficult, but it's just addition. You can do it with ease. You need to be a little less sloppy than I am because I've done this so many years. There was a time, probably 25, 30 years ago, I could do this stuff in my head faster than you could put it in a calculator. And it comes from practice. I mean, 5 decades is a long time to be doing the same thing. And if you don't become fairly competent after that length of time, you probably ought to hang it up and go try something else. So hopefully this helped. This is your introduction to the mobile concept.